So the software stack is what unlocks the power of the wafer scale engine and the hardware. And large scale science, as we see it in our context, is fundamentally about applying compute to ideas. And that comes from three things: the computational power, obviously the table stakes, which unlocks and gives you speed of iteration, but you need to ensure that you don't sacrifice flexibility in doing that. So first, in computational power, Nick showed off some of the raw power of the CS2 with the unbelievable amount of cores, the memory bandwidth, things that just haven't been done before. We have native unstructured sparsity support for blazing fast training, out of the box ability to support long sequence lengths, like easily upwards of 30,000, 50,000 tokens with no memory limitations, no workarounds, no changes to your code needed. The disaggregation of that storage and compute allows for larger, more ambitious models of hundreds of billions or even trillions of parameters, and importantly, speeds up your workflow as you're doing maybe small scale experiments with 40 billion or 40 million, 100 million parameter models, and then you can scale right up. And I think the software stack puts that power into your hands through our scalability, our usability, and our performance. So you're going to see in a moment as we walk through a few code snippets almost about how you can scale up that compute, how it's just changing a single parameter in a run command, how scaling out to 2 nodes from 1 to 2 at ALCF or in other contexts to 4, 16, 32, or hundreds is just as easy. And scaling up larger models only requires a simple change to the hidden size, the number of layers in a YAML. From a usability perspective, there's no use having a Ferrari in your garage if you can't drive it. So commonly used performant models from the open source are already defined with dead simple configuration files and a run.py interface. We train those models strictly data parallel, so there's no distribution code required by you, which we'll talk a little bit about later, how much that reduces the onus. And then that performance comes baked in. So you don't have to have layer upon layer of optimization built in. You're just getting it. So again, you get to focus on your end goal. And finally, in the flexibility, researchers need programmability, right? Some of our industry customers certainly want to just adopt the latest architecture, take on the latest research, but they want to scale training. They want to go immediately. But we recognize that you need more. We support, of course, the common architectures like GPT-2 and 3 and J, but we allow you to swap in and out those architectural blocks, those positional encodings like Alibi or activations like Sweeglue. But we also, at a level deeper, allow you the ability to port your code with us, via our PyTorch API to directly support PyTorch ops and make whatever changes that you need. So all of this, from how to get set up on a system to tutorials to train your first Hello World model, how-tos for the Cerebras specific features, or machine learning best practices that our research team is finding, as well as full examples on porting your models at various levels of abstraction, from a high level to full customizability, are all available in our documentation that, thanks to feedback and usability from people like you, has gotten a nice overhaul lately. So please, as you get on the system at ALCF, as you experiment, as you find new use cases, new opportunities, please give us that feedback. Now we can dive in. So how do you go from an idea to code to training a model? We integrate closely with PyTorch. So if you look at this diagram on the right, in the light orange, we have the common reference architectures and models of common sizes. So you can go from the 1 billion parameter version, the 7 billion, the 65 billion of those models that I think you'll see out in the open source. We help run those models through our run scripts. And if you want to customize, that we'll get into, we support PyTorch operations at a low level. We allow you to use our layers API to stitch together layers in a network, just as you would stitch those together using native PyTorch. And now as we move lower in that diagram to the pink portion, the compute graph is traced. It's lowered to our compiler, matched to either handwritten performance kernels or auto-generated kernels. that hits our placement and our routing engine and finally meets the wafer scale engine. And we're an active contributor to Torch MIR and the open source community. And with this PyTorch integration, your code, your workflow is just going to feel the same, right? We handle the lowering, we handle the distribution. You're not worried about those complex forms of interconnected pipeline or model tensor parallelism. There's no refactoring needed from small experiments to of 100 million parameters to large ones of 100 billion. You can spend more time focusing on analyzing results, on designing experiments, on testing hypotheses. And so the takeaway here is that you get to have a feeling of programming a single node while actually unlocking the power of a multi-cluster AI supercomputer. Great. So what does this actually look like in practice, right? So first, we define the model. So you can write it in a high-level representation, in this case, PyTorch. You can define or adjust the parameters in an associated YAML file, and you're writing a logical model for a single device. Now, as you can see at the top right, we've got a GPT-3 XL 1.3 billion parameter YAML, or at least a small portion of it. You just define the hidden size, number of hidden layers, number of heads. And there's a bit more to it, but not much more. Now we get to move on to training the model. Now at the bottom right, within our public model zoo, each model has its own run script. You point within that in the orange here to our model params file. You define the number of CS2s you have access to for this run, whether it's 1 or 2 at ALCF or even more in other situations. These clusters can be segmented. So we have larger clusters of 16 and beyond CS2s that aren't necessarily only used for 16 node runs. There can be 8 node runs, 4 node runs, 2 node runs ongoing on the same cluster. You then specify the number of steps, point to where your artifacts need to be stored, and then finally define whether you're training or evaluating. So again, really simple. You get to see everything, you know what you're doing. And then scaling is immensely important to us because you don't always want to train on a single system because it's not fast enough for the speed that you require. The disaggregation of model parameter memory and compute that Nick just talked about allows us to scale compute in a really powerful but really simple way. So if you look to the right, you'll see the simple parameter change in your run command is going to give you access to however many CS2s are in that cluster, right? 1, 2, 4, 8, 16. Nothing else has to change. No extra code is being written. So no matter whether you're training on 1 CS2 or 100, your model definition doesn't change. You're writing no distributed training code. You're doing no refactoring, and the code you write for your initial experiments can scale as large as you need it to. And again, with the appliance handling this fully data parallel training, you spend more time on analysis, more time refining hypotheses, more time researching, and less time spent engineering, which is great, but not necessarily what you come to our systems to do. So not only scaling out to more compute, but if you want to scale up in the number of parameters and size of your model, that's simple too. At the top right, we see an example YAML for GPT Neo X. So we got 20 billion parameters rather than 1.3. We're again just changing the size, the layers, number of heads, and we're off to the races. Again, same flow, fully data parallel training. Your run command points to a new config file. You increase the number of CS2s as necessary. Now you could run it on fewer CS2s, but then time can sometimes become a factor. And so with GPUs, small models come free, and then large models come at this great cost of time and complexity. But with Cerebras, the large and the small models both come free. And we were just curious. So to illustrate the point of how much simplification we've done from a software level, our research team walked through kind of all of the major distributed training and scaling frameworks, from Meta to NVIDIA, Google, Mosaic, and Microsoft, who have all done fantastic work in this area. And on the y-axis of this chart, you have lines of code. So as you can see, it's tens of thousands of lines of code to distribute these models over, say, 1,000 GPU cluster. But our software makes training 100 billion parameter models as easy and simple as that 1 billion parameter. So the hardware has the complexity, the architecture is complex, so your user experience is extremely simple. And as an exercise, if you look to that very small orange bar on the right, one of our teammates decided to build Cerebras GPT Nano, kind of inspired by Andre Karpathy, ML researcher, and his Nano GPT implementation. Now, Karpathy's implementation is a great teaching tool to dive into decoder-only language models, but it caps out, I think, at around 124 million parameters, right? So only trained on one DGX node. At Cerebras, our similar code base size Cerebras GPT Nano, nano here being in air quotes, that can scale, can support models hundreds of billions of parameters for 1/30th of the code base, meaning less effort, faster iteration, and faster experimentation. I see there's some questions coming in to the chat. I think Vishal's answered some of those up front, but please keep asking them. And then finally, hand in hand with the ease of writing code to scale large training jobs, we promise to give you that performance, right? So there's this accessibility. You have the ALCF CS2s, there's the usability from the software side, but we still deliver on that performance. So if you only have access to one CS2, you can still train some of the largest state-of-the-art models. But when you want more compute, when you want to scale out to more CS2s, you still maintain that near linear performance. And here you can see just how close those dots are for performance of GPT-3, J, GPT Neo X, both at short sequence lengths like 2K or standard, and the longer sequence lengths of 10K are giving that near linear performance. Nobody wants a performance drop-off, neither do we, and we think that we're giving you the scaling that you believe you're getting, right? For each additional unit of compute, you should actually get that performance. And then we also have a question right now, do we support Keras and TensorFlow? We saw there's some really neat updates to Keras as kind of a front end for PyTorch, TensorFlow, and JAX. That's quite new. We're still evaluating it. We previously supported TensorFlow, but frankly saw much more demand moving toward PyTorch, so have focused a lot of our efforts there most recently. But we're always happy to hear feedback on how much one is being used at the other. That's something we're always trying to reevaluate for our users for our interface.